I'm Pallfy, a PhD candidate from TU Delft, Intelligent Vehicles Group, led by Gavrila, and I'm here to present our paper, CNN-based road user detection using the 3D radar cube. Our paper presents a radar-based moving road user detection algorithm. The algorithm is multi-class. It detects pedestrians, cyclists, and cars. It is able to provide this classification information both for each target individually, so at the target level, and at an object level. And it is single frame, which means that it does not need to accumulate sensor data over time. A commercially available automotive radar outputs a 2D point cloud of radar reflections, or also called radar targets. Each of these targets has a 2D position, a radial speed, and the radar cross-section value, also called RCS. You can see a top view of such a point cloud here on the right, and the same point cloud projected to the camera view here on the left bottom. These point clouds are rather sparse. For example, this bike just next to my head has only 2 reflections. The commercial pipeline to process such a point cloud and to detect road users with radar goes like this. First, you have the target list or point cloud presented in the previous slide. Then you perform some kind of clustering which tries to group reflections coming from the same object into one cluster and reflections coming from multiple objects into separate clusters. Then you extract features for each of these clusters and classify the clusters. So features are extracted per cluster and classification is also done per cluster. This pipeline works just fine if the clustering is performed correctly. However, this clustering step can introduce errors as well. For example, one can undersegment the scene, which means that you have less clusters than objects, or one can oversegment the scene, which means you have more clusters than objects. An object is split into multiple clusters. Or another problem that can occur is that there are too few reflections on an object and it doesn't make it into a cluster at all. A lower level of radar data is called the radar cube. It has 3 axes: range, azimuth, and velocity. One cell represents reflectivity at that given 2D position, range, and azimuth, and the given velocity index, which represents a speed. A column of the cube at a range azimuth index contains the full velocity distribution at the 2D location. Let me give you an example. Let's take a range azimuth cell, and let's assume there is a pedestrian in it. This pedestrian is not only moving with a single velocity, but also has a slightly slower foot speed and a slightly faster arm speed as it swings behind his or her body. This speed distribution is class characteristic since it depends on what kind of moving parts does the road user have. For example, I just presented how a pedestrian would look like in this speed profile, but you can also imagine a cyclist which has wheels and pedaling patterns, or a car where there is one single peak of speed as the whole body of the vehicle moves together. We propose a method which exploits this speed distribution from the 3D radar cube for road user detection. Let me give you an example of how it works. Here's a bike with the radar reflections overlaid in the camera view. And here is the 2D projection of the radar cube of the same scene. So it's only range and azimuth now. The velocity axis is summed up. You can see as the radar targets are overlaid with the blob in the radar cube. To exploit this low-level data, first, we map the radar targets to this radar cube, both in the 2D location, so azimuth and range, and in the velocity dimension. And then we crop a 3D block around them. So a part of the radar cube is cropped. Afterwards, the target itself and its cropped block are both fed into the radar target classification network called RTCNet. RTCNet is a CNN, a convolutional neural network, and it is designed to classify each target individually into the following classes: pedestrian, cyclist, car, or other. As you can see, the target and the cropped cube goes in, and the classified radar target comes out. On this image, we marked cyclist classified radar targets as red. After classifying each radar target individually, we also perform a class-specific clustering. On this image, you can see the grouped together radar targets inside this cage, which means that these targets are not only recognized to be from a bike, but also to be from the same bike. There is a big advantage of doing this class-specific clustering, and that is that we can use different clustering parameters for each class. Let me remind you of this slide where we presented the potential error sources in clustering step. In the conventional pipeline, you have to use the same parameter for all classes, which can be too small for big objects or too big for small objects. Instead, in our pipeline, you can first perform the classification and then the clustering. Let me show you two real-life examples. Here we present two scenarios with both the baseline method, Schumann 2017, and our method in the bottom row. On the left, you can see three pedestrians which were unfortunately grouped together by the baseline method. Here's the top view of the radar reflections. But our method was able to separate them into three individual objects. On the right, you can see a car in the front and a bus in the back. The baseline method divided both vehicles into multiple clusters. However, our method, using the class-specific clustering parameters, was able to keep the reflections together, which belongs to the same object. So it created one cluster for the car and one for the bus. Let me show you some qualitative results on videos. Here is the target level output of our algorithm, so no clustering was performed yet. On the left, you can see a bike, and all reflections coming from its frame are correctly classified as bike. On the right, you can see a pedestrian with several correctly classified targets. This is from our test set, and the camera is only used for visualization. Here is another example. We drive by of bikes on the left, which are correctly classified as bikes, and you can also see several pedestrian detections. The method also works in several lighting conditions, for example, in complete darkness. Note that a camera-based detector would have troubles here. Finally, let me present the object-level output of our algorithm. Here, radar targets are not only classified, but clustered together into individual objects. Note that both smaller objects, like pedestrians, or larger objects, like bikes or cars, are clustered correctly. That means that we have a better idea of the size and position of objects. In front of our ego vehicle, there are three pedestrians correctly classified and divided into three objects. There is one crossing the street, and there are cars and bikes passing our ego vehicle. Thank you for watching our video. For more information, please visit intelligentvehicles.org or contact me at a.pallfy@tudelft.nl.